Hello, good morning. So thanks for coming today. I'm going to present the paper HalluciDet, Hallucination, RGB modality for person detection through privileged information. So this is the authors of the paper, me, Fidel, Messi, Toma, Eric, and Marco. So Eric and Marco are the advisors of the paper. So this paper was accepted on WACB 2024, and it's a collaboration with the stack, and we also have some scholarships from MyTax and Compute Canada resource. So this is the.
Thank you for this video.
Yeah.
I think it's a shortcut.
Thank you. So this is the outline of our presentation today. First, I'm going to start the background and motivation, then the related works, our proposed method, the HalluciDet, and then the conclusions and future works that we are targeting to work in the next months. So here is the background and motivation. So in object detection, we have as input image, and we want as output, for example, the class and the bound box of the objects that we are targeting. And especially in multimodal cases, for example, we have like some different modalities that work in different spectrum of light that we can see. For instance, for example, we have the RGB that is mostly used in the day. And for example, we have the IR that you can use, for example, for surveillance and in the night situations. So it's different spectrums of the light that we can capture with different sensors. So for example, if we use like different sensors to capture the same image, we can, for example, see that in IR for night vision, we have like persons that is more easy to see and to detect. Then, for example, if you use only the RGB, so we have like sometimes the complementary and sometimes additional information that can be used by both modalities to increase the detection. And also we have some effects. For example, there are some materials that that the infrared sensor can capture when it's reflected. So for instance, the infrared here is emitting some information that we can capture with the sensor, but it's like a reflection on the material here. In the RGB, we don't have this, so it's like some information that the detector needs to remove during the detection. So we don't want to detect this kind of effect. So the applications that we can use multimodal, or for example, we have like the IR together with the RGB is like, for example, self-driving cars, that the car needs to detect, for example, pedestrians or cars and needs to move and do the self-driving. And also, for example, smart buildings, where we need to control the device inside some rooms to, for example, control the light and measure the temperature of the room. So we can use this kind of sensors that capture IR to detect people, and we control the environment. Some of the related works about how we can do like adaptation on the RGB. The motivation of this work is because it's really common to have RGB models over the web, and we have not so much like big pre-training models on IR, and also what's called foundation models on IR. So the motivation of this work is how we get like the RGB models, and we can adapt to this new modality that we want to target, like the IR. And in this case, we have like this work from Herman that they proposed to do the adaptation on the input. But this method was using like just classical computer vision, where they try to pre-process the input image, doing some translation and also some augmentations on the input image, but using just like inverting the pixels to make the IR more close to what's an RGB distribution. And they use in a frozen detector to see if they can just get some detections, and also they try to fine tune also the detector, and they saw that with this kind of approach, just inverting the pixels was a simple baseline to do the adaptation of this model. We also have some models that are kind of generative image level, that they try to learn some distributions between a source and a target data. For instance, the GAN, you just provide, for example, 2 different distributions, and they learn how to translate from one modality to the other one here using the cycle GAN, for instance. But this kind of approach, they put a lot of artifacts in the generated image, and it's also not so stable to train. So it's really hard to have a good translation that works in all the cases, and especially because it produces a lot of error on the target image. So our proposed method, we are going to do that in a way that is better for the detection. So we train what we call hallucination network. It's a model that's going to translate from one modality to a pseudo RGB. That's not exactly, we are not targeting this image here to look like an RGB image, but we are targeting the final task, that's the detection. So to train this hallucination network, we have a frozen RGB detector, and then we just backpropagate the hallucination loss, that's the loss of this information through the RGB, to train our generative, not generative, but translation method. So in this sense, this network is learning what's the best information for the detection. So that's basically the main idea here. In our setup, the RGB detector was frozen during the training and also during the inference. So you just need to use this method here, and you don't lose the information also in the RGB modality. So if you also want to forward the RGB, is just like a selector. You can just forward here, and you have the modality working for RGB, and you also have the modality working for the IR. So basically, we compared with a lot of different methods. And these methods is basically what I showed as baselines, that they use like classical computer vision approach to match the distribution of the RGB. And then they forward on the detector and just see how it's going. So we did that for different detectors of different families, like one-shot and also two-shot detectors. And we also tried to, with different generative models. So we tried with CycleGAN, cut and fast cut is a different methods using contrastive learning. We tried with UNet, and also our method that's just like a hallucination network. That's a UNet backbone composed with the detector, and we trained this with our hallucination loss. So here is our result also with this adaptation for different detectors. In almost all the cases that we tested, we have some good improvements compared with no adaptation. Here is just the evaluation on the IR, on the detector. And fine-tuning is just like we get the detector and we try to fine-tune with the IR. And we see that we can improve in several cases. We also tried to decrease as much as we could the hallucination network, because as I told you, the hallucination network is composed of a UNet model that's trained with the detection loss. But this is also costly because we need to increase the number of parameters to do the training. So we did an experiment how we could stress as much as we can the UNet in terms of number of parameters. So we reduce it, and you see that with like a mobile net backbone for the translation network, it's enough to get some good improvements compared with just the detector. We also did some kind of experiments for different IR datasets. And we saw that for 2 different state-of-art datasets that are really used on the community, 2 different benchmarks, with a small number of training samples, we could also reach the fine-tuning. So it's also something interesting that with like for the LIVIA-ETS, with around 20% of the samples, we can beat the the fine tuning. Yeah, we are close to the fine tune here, and we did like 40 more or less. And for the FLIR ADAS, we are close to the fine tuning, and around 50% we are better. So if we reduce the training number of samples, we can also be better than the fine tune. So this is pretty interesting. We have some visualizations. One thing is that we don't constrain the output of the hallucination network. So it's just the detection loss that's used. And for this is kind of the image that we generate during this process. So for each detector, it has its own loss that is trained. So the output that you see is different for each detector. And we are not targeting the image quality. So we are just targeting the detection. So this is what the detectors see and think that's important for the final detection. So this is for another data set, the FLIR. And this is just a GIF. So this is the detection on the RGB detector, and this is the detection on our method. So we can see that sometimes, for example, our method is more precise, and we have some, for example, here, some false positives. That's because of the RGB modality. So in conclusion, we propose a novel approach that leverages this information of the RGB detector as a pre-trained model. And we guide this information to train our hallucination network. So we were the first ones proposing this for detection. So to train for the final task, no one has done this previously. Normally, they just do the image translation, and then they, for example, train a detector, or they try two-branch approach. So this is one thing that was like novelty. And the other one is that our work is really straightforward to use. It's simple. You just need to connect this unit, and then you just train your detector with that, and we have like good results. So this was also good. And for future works, we also want to try for totally unsupervised scenario, because for this we need some annotations on the IR. So we want to remove the labels to train the model on IR. We also want, for example, to see if we could do the translation without do the adaptation for the RGB of the same data set. This is something that we are trying to, for example, if you get from another pre-trained model, like a big foundation model on RGB, could we do this adaptation more easily with our approach? So it's something that we are interested to explore. And yeah, that's it. If you want to talk or discuss more, you can reach me here. Here is the code. If you want to get the code, just scan this QR code. It's gonna work. No one's gonna scan.
Right, thanks a lot.
Yeah.
Thanks. So thanks for keeping it short. So for those who are late, it's a practice for wacky talk, and feel free to, we're in a family here, feel free to provide comments or tough questions that can help him improve the talk. So please, are there any questions?
How are you?
Good.
Good.
Very good presentation. Just one question about the future work. If you, for example, didn't use the labels, it was kind of unsupervised. Do you think that having some sort of let's say regularization on the generated images from the hallucinator would work? Because probably you can make, I don't know, for example, you can take some statistics from the training data that you can use so that the generated images look more like RGB. I don't know if that could be something that you have thought of or not.
Yes. Right now we are testing to do with sub-training. So basically we just forward the same way that we are doing here. And we try to also forward the IR on this detector to see if we can use like some pseudo labels to train. It's not working that much. So we also need to explore more this part. But But yeah, I think that we can also do some regularizations, as you said. I was thinking also, for example, if you see this part of the method here, we could try also to do some regularizations on the output, as you said, and we could minimize, for example, on the IR to this part here, like L2 regularization or LPIPs to make like a perceptual loss here to make like more qualitative, better for visualization. And then the detector could like just learn what's missing on this kind of image, because if you see the IR is not that far from the RGB, but yeah, we need to export to see if this could generate like good pseudo labels to use. Okay. Thank you.
I think you said that first, thank you for presentation.
Thank you.
You said using some privileged information, but in the slide you didn't mention what is the privileged information.
Yes, nice question. First, depends on the point of view, but here I consider the privileged information of the information that we have privileged on the detector. So this detector that we trained here is trained on the RGB from the same data set. I mean,
you mean that the knowledge learned from the other data sets you use as a privileged information?
Yes. So this I call privileged information, but I know that in the literature of the privileged information, normally they try to distill the knowledge between like a.
But I know because I'm also working on the same topic as the privileged. I wanted to mention that what is the privileged information?
Yes,
because you use in the title.
Yeah, is the knowledge that comes from this detector. So the labels that we are comparing with the knowledge that we forward from this input here, we are going to backprop. So yeah, it's like a distillation of the knowledge of the data.
And also because the nature of P is that you don't access to that information in the testing time.
I see.
And I mean that you need to mention that in
the
inference time you don't use the RGB detector.
Yes.
And also for did you test? You said that inversing the RGB spectrums to estimate the infrared. Did you use instead of reversing using some random between spectrums? Because when I tested use as augmentation between RGB and infrared, I found that when I use random combination, it makes it better estimation of negative, because infrared values depends on the material and depends on the color.
Mm-hmm.
Then you reflect the infrared, it depends on, for example, black absorb more, but depends on, for example, latex. If that the material was latex or leather, it's reflects the values. I mean that it depends on two type of aspects.
Yeah, for this scenario, I just tested what I saw on the baseline paper. So basically, it's like inverting the pixels, trashing the histogram. So this kind of simple things. And we compare with like more learning methods like CycleGun, cut, and fast cut. Is like two more recent methods that is close to CycleGun, but using contrastive learning are more recent. But I didn't play like, as you said.
And also for the last question, your translation network, what type of constant you use for preserving the edge or output image to the input image?
Here I don't use regularization on the image. It's just like the only thing that I do here is because normally I use this backbone as a traditional segmentation model. So you need to change the output of this, because normally in segmentation you need the C channels to be the number of classes that you want. So basically I change this to be 3, and I also add the sigmoid. So it's gonna be like 0, 1. So it's just already normalized. So I just input on the RGB detector.
You mean that the output of your network is 1 channel images?
3 channel. I consider 3 channel, and then I use directly on the RGB detector. Otherwise, I would have to reset the input here of the detector, so we are going to lose some information.
Then I wanted to know how the model is able to preserve the edge. I mean that when you use, as you said, when you use generate model, it's at some artifacts. It lost the details.
Yeah. Here in this case is because, for instance, this network is already pre-trained also, so it's not trained from scratch. So there are some knowledge of this to do the translation, but it's pre-trained on like segmentation tasks, not like translation from modalities. And also when I incorporate here, I have like a classification and a regression loss that's from the detector. So this is gonna guide our method to train. Our hallucination network is composed of two terms. One is the classification of the detection, and the other one is the regression. So we need to play with this. And we see, for example, that if we put more information on the regression, it's better for the localization. But for the classification, as the detector was already pre-trained on the detector, doesn't make too much difference to put a high classification part.
And just the skip connection that you have in units, kind of like mitigate the issue of the noise.
Because yeah, the hallucination backbone is composed of also some residual connections that help on the
okay, good, thanks.
Thank you.
There's some questions from online. So, well, Christian also commented, congratulating you on the paper. I know you won't see that later.
Thank you.
But there is Esan from online who's asking a question. I don't know if Esan, you want to ask it? Like you're welcome to turn on your microphone and ask, or I can read it. I'll read it. Okay. So Esan is asking. Maybe he doesn't hear me, but he's asking what causes false negatives in HalluciDet. And then I don't know if it's follow up. How does the RGB detector affect false negatives in HalluciDet? Okay. Yeah.
So on the HalluciDet, normally is when you have like some problem on the gradient of the training, because if you see the quality of the image that we are generating can be seen as like a adversarial image, because we don't put in constraints on the image that we generate. We just like train for detection. So if these images that we are generating are really noisy, the detector, even though it can detect something because of the privileged information, but it's not going to work for all cases. So these also impact on the false negatives and false positives that we have.
Maybe one more from my side. So if you go to slide 15, and like the results are nice, except for that one case with RetinaNet and fine tuning. I don't know if you have any insight there. Why is that? Why is the performance much higher there in that particular case?
Good question. We try to investigate. We don't have like a clear definition why, but basically there are different kind of detectors that we are using. So each one basically is from one family of the detectors. And for the RetinaNet, we couldn't beat on the fine tuning also. Okay. So it's something that we tried, and we think that maybe we can improve with more regularization in of the image that we are generating. Because it depends on when we are doing this kind of approach, it depends on how good the model here is gonna detect. So if you have like a kind of privileged information, as we said before, that's not good, we cannot train this model well. So all knowledge that we need is coming from this guy. So if it's not good, it's gonna impact the training of our method. But if you see, for example, the one with the faster RCNN, as the method by definition was really good on the image that we are generating, it was enough to improve the result.
Yes, I don't see.
Your screen marker raises his hand.
You want to help here?
It was the same question as Eric asked. So, yeah.
Oh, thank you.
But I think if we're flagging that, maybe you're likely to see that as a question.
Yeah.
And maybe a way to prepare is maybe to have a few like low-level examples that show where it does better or worse. That could help you explain.
Yeah.
For
So
that particular case,
yeah, for instance, if you see like this image, the ones that are generated for the other methods or other detectors are not as good as the one that is generated from the faster RCN. So this also is because of the privileged information that we are distilling. So these impact also the detection. That's why some mechanism that to regularize it better, the output can also improve. It was something that I played a lot on the GTA 1032 and 1031, but then I put inside and was just trying to see if I could train like the whole pipeline, and then we could also improve on that, but we could like put more things to increase. But in this case, I wanted to show that just with like a simple thing, it works, and then we could iterate more on the ideas.
Okay.
Yeah.
I just wanted to, do you have a baseline that would be fully trained on IR just to get sitting on what you should expect to do next?
To train it, I have just fine-tuned, as I showed, but full train from scratch, I didn't put on this table because I just consider like if I grab like normally the people grab a model from web and they grab like pre-training on Coco. So all these methods here are starting from the Coco. So it was to be more fair, I went to this direction, then to try to fine tune from scratch everything and compare it to mine.
Like a question, but have you ever tried to continue training by adapting the detector?
Yes, it's also improved. We have some results, but we didn't did on this paper because we were seeing if we could like just beat in this setting. But for example, we are doing, because to do on this setting of fine tuning the detector, we would open to a different kind of fine tuning. Normally in the new detector, they are using, for example, LoRa to do fine tuning or this kind of new techniques. So to that, we should have like a bunch of things to compare. So we try first to do on this direction and try to iterate to more ideas that we could, for example, fine tune. But we have like small experiments that show that we can increase also if we unfroze the detector.
Any more questions? Well, otherwise, let's thank
you.
Move on to next one.
Thank you, Heitor.